basis. This part is from section 4.3 and 2.9. After this lecture, we're going to define and understand rank, dimension, basis, rank theory. So given a vector space, for example, Euclidean space Rn, we know R2 means a plane, R3 means our living environment. So Rn means usually collection of all vectors given by a column vector with length n. Then we usually refer this n as dimension. Then what do we mean by dimension? So to define that, we first define basis. A basis is a set of linearly independent vectors that spans the whole vector space. So for a vector space, you can find a basis, but may be different from my basis. So there may have different bases which can span the whole vector space. But no matter what basis is, the number of vectors in the basis should be the same. So that defines the dimension. The dimension is the number of vectors in any basis. So for example, in Rn, we can find standard bases like this. So 1, 0, 0, all the way to 0, 0, 0, 1. Rank. Rank is a concept for a matrix. So suppose we have matrix A. What is the rank? Rank is the dimension of column A, column space of A. We've discussed column space of A in the last lecture as following. So suppose A is given by A1, A2, AN, those columns, those are column vectors. Then column space of A is span of A1 all the way AN. Now what is the rank of A? Then this is dimension of column A. So the rank of A is dimension of column A. So if a given matrix A, if you want to find rank, then you need to find the basis for the column space A and count the number of vectors in the basis. So to do that, what we do is two-step procedure. So first, I want to change A into REF, and then form a basis by the pivot columns of A, not pivot columns of REF. This is very subtle point, but we have to be careful. At the end, the bases are given by those vectors in A, not in REF. So let's look at this example. We have the same matrix as in the previous lecture. So I'm going to copy this down. So we already reduced it into REF. So this is REF for A. After many EROs, we can get this REF. And we have two pivots. And what is basis for the column A? Then the bases are given by vectors of A with pivot columns. So the basis has two vectors in this example. And what is dimension of this column space? Then we can say dimension of column space of A is 2, which is rank of A. And find the basis for null space of A. For this question, we can still use the last one. So we have null space of A, which are given by 3 vectors from PBF. And those automatically gives linearly independent vectors. And null space of A has null space of A, its dimension is 3 because there are 3 vectors. So find the basis, then the basis is indeed from here, so these 3 vectors. This is basis of null space of A. And what is the rank of A? We already mentioned that rank of A is 2. And justify the rank theorem. What is the rank theorem? Rank theorem says dimension of column A equals dimension plus dimension of null A is the number of columns of A. So we said dimension of column A, which is rank of A, is 2, plus dimension of null space of A. We have seen that 1, 2, 3, so this is 3, and equals number of columns of A. 1, 2, 3, 4, 5, so 5. And this is not a particular example. This actually gives the rank theorem. No matter what A is, with different A's, you always have this relation, rank theorem. All right, at the end, we are going to conclude this. So with invertible matrix theorem. So for a square matrix, one of the important concepts is it invertible or not? If this is not invertible, then we call this A is singular. And then there are many ways to restate equivalently for invertible matrix. And one of the important point is when you have, if you A is invertible matrix, then it is equivalent to have A has n pivot positions. So whenever you have been asked a given matrix A is invertible or not, then you want to reduce it to REF and see how many pivots are there. So if there are n pivots, then that means it is invertible, and we can answer all questions related to this.